All right. Thank you, everyone, for coming. I hope your Data and AI Summit is going well. Sorry for the delay. We were waiting for the moderator. So what I'll be talking to you today about is foundation model serving, and specifically how we optimize performance for it. Just to give you like an initial introduction, Databricks has something called Mosaic AI model serving. It's this unified deployment and governance platform for deploying model endpoints, agents, all these fun things you can play with. It's secure, it's highly available, it's natively integrated into all of the Databricks pipelines and so on. And I would encourage you to go check it out, but I'm not really going to talk a lot about this. I'm going to focus on the foundation models aspect of it, which is the large language models and the other generative AI models that we host ourselves and optimize ourselves. So why should you care about these? We've seen a lot of rapid growth recently in usage for these. So personally, I'm not a big believer in AGI, ASI coming anytime soon, but there is a lot of emerging patterns we've seen for enterprise and data analysis use cases where these models actually do really, really well. And so this is not the forum to share our usage numbers or something, but suffice to say, like we've seen exponential growth in the usage of these models. And if you've been at the other keynotes and other talks here, you'll see a lot of higher level products that are being built. And if you drill down deep enough, there's an LLM sitting under them. So things like the bricks, the agent breaks, AI functions, there's a whole host of other products that we're building. At the same time, what we're trying to do is we're trying to stay at the forefront of performance for these open weights models. And if you look back, if you look at some of the workloads that we care about, that we see our customers care about, there is a big gap between us and sort of out-of-the-box DIY deployments of ELM or something, or other competitors that we're not going to name on the slides, but are some of the leading competitors that we have in the field. There's also a lot of velocity. We've been improving performance rapidly over the last 6 months, so something like 3x in some of our benchmarks and some of our models. I think there's another 2 to 3x to go in the next couple of quarters, so there's a lot of improvement happening. So we're improving, usage is also growing rapidly, so we're trying to keep up with that usage. The rough agenda of the talk today is I'm going to talk a little bit about the challenges, what makes these Gen AI models special, as opposed to just serving other classical AI models and so on. I'm going to give you a quick primer on LLM inference, just so everybody's on the same page. Then we're going to go a little deep, talk about optimizations that we worked on, and then come back a little bit and sort of talk about how we think about balancing performance with quality. Like you can go very, very fast if you don't actually care about the quality of the text you generate. So we spend a lot of time thinking about that balance. OK, so let's start with challenges. Anything that is sort of challenging in a classical AI model kind of gets amplified with these large language models that we're dealing with. And the first thing is they're large. It's right in the name. And they're getting a lot larger. Like the size of these models, the open weights models has been growing rapidly over the last 6 months or so. And when you look at the closed proprietary models, they're much bigger than what's out there in many ways, like the larger OpenAI models and Anthropic models and so on. Just the physics of moving these bytes between GPUs, CPUs, disks, downloading them as you autoscale, like it just makes things hard. And so one of the things, just to get the economics to be competitive, to get the performance to be competitive, you have to compress these models. There's lots of ways to compress them, and a lot of the basic ways actually lead to significant degradations in model quality. So you have to do this very carefully. And the other thing is, like, you have to serve these off hardware accelerators. Like, there's a lot of ways you can serve them off CPUs. You tend to make compromises in either speed or quality. You can't really build a serving system that way. In situations where, like, if you think of a classical AI model, like a classifier, where you can scale up relatively easily to hundreds of thousands of QPS on CPUs, we're trying to scale one of these LLMs to tens of QPS. You absolutely need very expensive, very high-end hardware accelerators. And finally, there's multiple bottlenecks in the system. And you really have to do these cross-layer optimizations. You have to co-optimize the CPU code with the GPU code. You have to co-optimize the design of your distributed system with how the servers work and where the bottlenecks in the servers are. And so all of these challenges make setting up one of these LLM inference systems fairly hard. There's also another aspect of it, which is there are very strong economies of scale in serving these models. If you just take something like a Llama 4 model, serve it on your own private H100, it can be 10 times as expensive, depending on your workload, than something like Claude or something. So the models themselves have a very high fixed cost. So you sort of need to amortize it across users. You need to like have a multi-tenant system that can really exploit the fact that the hardware is pretty powerful if you can batch users together. And once you start scaling up, it unlocks a whole host of new optimization opportunities. Like you can have differentiated servers, which is a prefill decode disaggregation. You can invest in techniques like low-rank adaptation or like parameter-efficient fine-tuning and stuff to sort of concentrate different fine-tuned models on the same server. But there's the flip side of it. When you're building these serving platforms, simplicity is very challenging, right? If you just look at the inference engines out there, the models out there, there's tens of models, hundreds of flags, very nuanced interactions between different features on these. And if you're thinking, I want my own LLM, it's very hard to account for all that, get it right. There's a lot of complexity you have to pay for upfront. So our perspective has been, we just want to build something that just works from the perspective of the user. You do an SQL query, it just runs, it auto-scales, performance is great. You talk to an endpoint, it works. You don't have to think about what the quantization scheme is, what the hardware is. Like all these things are sort of tuned to be the best given the sort of workloads that we see on Databricks. But underneath it all, I think we have to start with a very strong investment in our core platform. So performance is super important for LLMs, but at scale, you cannot be performant unless you're reliable. You cannot be performant unless you're highly available. And so all of that, underpinning all of model serving, is a very strong infrastructure foundation. And then what we do is we integrate the best-in-class open source innovations where, like anything that comes out, we're like, okay, if this is faster than what we have, let's just pull it in, let's use it. But then we find a lot of gaps in open source and other things that we have access to. And we do a lot of deep research, a lot of deep engineering to overcome and go beyond what is achievable out there. And so that is kind of what I'm going to spend the bulk of this talk talking about. But before I can go deep, I need to just give a quick overview of LLM inference. So at the heart of it, you've probably heard about this. LLMs are regressive. What that basically means is you just do one token at a time. So if you're trying to generate a string of text, as far as the LLM is concerned, it's a sequence of numbers, tokens. And you start with your prompt, and it generates one token, feeds it back into the model, generates the next, feeds it back, generates the next, and it just goes on until it generates an end token, or it runs out of whatever token budget it has. That is the basic process. Now, there's some important implications there. Because it's variable length, you can't predict how long this is going to be. You can't do smart load balancing and stuff up front. It has to be reactive, because you don't know how much work a prompt is going to take. It also has implications around how you do, I'll talk a little bit more about that. Another thing that comes out of this autoregressive nature is you're running the same model multiple times, right? Most LLMs are basically stacks of transformer blocks, and when people talk about it, they'll give you like a scary diagram like this sometimes. There's lots of little components. But the things to take away from this are the model itself is basically a stack of the same module stacked on top, like 20 layers, 30 layers, 80 layers, depending on the model, right? And you're doing it in a loop. And there are things you can cache within those blocks. So this is when you hear about the KB cache. There are vectors that you compute on the first pass that you can just reuse in the next pass instead of recomputing them. And what that gives rise to is like you have to maintain a sometimes very large KV cache to achieve good performance. What that also means is because when you start a prompt, you have to compute everything, and then the next time, you only have to compute one token's characteristics, and the next time, just one more. So it gives this split of prefill phases and decode phases, and each of them has very different bottlenecks in terms of the hardware. Like prefill is bottlenecked on the compute capacity of your hardware accelerators. Decode is bottlenecked on basically memory bandwidth. And that gives rise to like different optimizations you can do. It gives rise to people splitting up these two things into different servers, so that one is optimized for one case, the other one is optimized for the other case. What most servers, this is sort of table stakes. Like if you're running any server right now, LLM server in production, you kind of have to batch requests. And the reason for that is on modern hardware, the hardware capacity of is way beyond what you need for one prompt, unless it's a very long context prompt. And so you want to be able to batch multiple requests, keep the hardware fully utilized. And then you've also got these random arrival processes, especially in a multi-tenant system, right? Your requests are coming in, you don't know when they're coming in. So as soon as a request comes in, you want to be able to integrate it into the batch. So that's dynamic batching, right? Like you want to be able to just add requests into the batch, grow the batch dynamically as requests arrive. And then there's something which most systems do now, which is continuous batching, which is you want to do, okay, so you're running decode, a new request arrives, you immediately want to put its new tokens into that batch. Another one arrives, you want to put it, so there's no clear separation between prefill and decode steps anymore. You're running these mixed batches as you need to, and it like creates additional complications and features you may have heard of, like chunk prefill and stuff, for sort of like managing how complicated this process gets. So yeah, so that is roughly all you need to know about LLM inference to make like reasoned judgments about like what different optimizations and stuff you should pursue. And then you need to know a little bit about GPUs, right? So the main thing you need to know about GPUs is they're a hardware accelerator that sits next to your CPU. The CPU submits work to it asynchronously, so it's just submitting like do this, do this, do this, do this, like run this matrix multiplication, run this nonlinear function transformation on it. And as long as the CPU is able to feed those tasks fast enough to the GPU, it's fine. The GPU just keeps 100% utilized. It just keeps doing that work. It's pipelined. If the CPU is too slow, you get bubbles, and that's kind of what I spend most of my time trying to figure out, how to get rid of very subtle bubbles within the GPU. There's also things like, there's bottlenecks because the GPU and the CPU usually don't share memory, and so you have to be very careful about how you're moving data and weights around, and if you do it wrong, it can have a pretty big impact on your performance. Okay, so that's sort of introduction 101 to what's important in this space. Let's get into more of like deeper techniques of what we do. But first, why do we care about performance? With Databricks, we could just launch a container, or you could just launch a container with VLLM and call it a day. It's kind of good enough performance. We kind of, at Databricks, we pride ourselves as user obsession, so we really want these responses to be fast. But then there's also this other side. I said demand is growing exponentially. Hardware and cost cannot grow exponentially, so we have to make the system much, much more efficient to absorb all that growing demand. And that has to be beyond what we have seen coming out of sort of open source and so on. Then there's also product co-optimization. Like we spend a lot of time on the performance team co-optimizing the performance in conjunction with our product and research teams, so that from your perspective as a user, you are like, oh, this is an agent break, I'm going to hit an optimize function. And you don't have to worry about like all the months of optimization that went under the hood to like make that 1/10 as expensive as using GPT and just as fast or faster. So when I think about performance, right, there's nothing, sometimes there's moonshots, but most of the time it's this very predictable loop where you profile something, you find the bottlenecks, you optimize them, you go back and you fix it, and you go again, and you find new bottlenecks. And that is kind of how we approach it. So we're working on some sort of more speculative things where we're trying bigger ideas, different model architectures, like a lot of stuff, because we have a research team. But for the most part, it's like just stack wins on top of each other. So you take techniques and you, like, if you improve scheduling, you get a 2x improvement. Then on top of that, you go in, okay, I've got better scheduler that is better at sending work to the GPU. I'm going to make the GPU more efficient, and that's another 1.5x, for instance. Then maybe, okay, let's do less work, right? And that's quantization. So you work with smaller numbers, the GPU can compute them faster. And then the third one is, okay, let's share hardware between users. And that's another 3x or so improvement in performance per dollar. And so all of these, if you stack them all together, you're sort of getting in the 10x range, right? But if you look at any of these individual things, it's like, okay, this is a few PRs or somebody spent a couple of weeks on this. So one of the things I will say is, if you look at the last generation of LLM inference engines like VLM V0 and so on, and the newer ones, which are much faster, sometimes 2x faster, right? The main difference has been this. They have optimized CPU overhead relative to where they were. In the past, what used to happen a lot is the CPU was doing complicated scheduling decisions, copying tensors, like all these things, and you pay 100 microseconds here, 100 microseconds here, a millisecond there, and you've eaten up a lot of time that your GPU could be doing work. And now that we've started optimizing this, especially because these engines tend to be written in Python because they're based on Torch, we are seeing a lot of wins. And so this is an example. I'm sorry for all of you in the back, but this is an example of comparing a naive way of doing this, where you just have sort of a single-threaded way. You compute something. You're like, hey, what is my batch that I should run on the GPU? Submit it to the GPU. GPU comes back with, here's some logits. You pick a token. You feed it back into the system, and you go again, right? The GPU is okay. It's kind of utilized, but there's a lot of dead space if you look at the bottom stream, right? But what you can do is you can build your system to be pipelined, use multiple threads, use multiple processes, do work out, CPU-heavy work in non-blocking ways, and then submit it to the GPU as efficiently as possible. And when you do that, you can sort of bring those GPU execution blocks closer together and get rid of bubbles, and that has a big difference on how much throughput you can get out of the system. And so this kind of looks like, if you all have used torch traces and stuff, this kind of looks like what you would see if you're optimizing a system. You're basically bringing the GPU blocks closer together. That is only part of the picture. Every time you ask the GPU to do work, a lot of the time there's scheduling overhead, just the way the work is submitted, especially on NVIDIA. And so there's ways to deal with that. There's CUDA graphs where you're basically trying to cache the operation graphs on the GPU side. They're pretty finicky, but when they work, they're really powerful. There's newer stuff like PDL, which is sort of getting beyond that. It lets kernels within themselves stagger and execute earlier, start execution earlier. There's also something that we have found particularly effective. If you look within these models, you often find parallel paths. Like, these are subgraphs that don't depend on each other. So the model splits off into two paths, and then it converges back together. And if you do some careful engineering, you can basically make those two paths execute concurrent in parallel on the GPU. This isn't as simple as just writing some torch code that splits them into streams. Most of the time, you have to do like kernel optimizations and stuff. But when this happens, the best case is you can completely hide the execution type in one path. So that's like a free lunch in some sense. Well, you've had to do a lot of work to get it working. But yes, it gives you a big speed up when it works. And so we've done a lot of this to optimize, say, Llama 4 or for PEFT. The thing that you will hear a lot about is, when people talk about performance optimization, is this idea of fusing and writing custom kernels and stuff. And basically, a kernel is just a task that executes on a GPU. And the fewer of them you have, generally it's better, because starting one of these tasks, every time you pay some cost, and starting it up, bringing it down. If you start up a task to, say, add one number, and then you start up another task to apply nonlinearity to the result of that, right? That can be done more efficiently if you just write a new task that adds one, applies the nonlinearity, then writes it out. You skip intermediate writes, you save scheduling overhead, and so that's basically the idea behind Fusion. And it's pretty powerful. It works fairly well. It requires a lot of GPU expertise to get this right. I'll talk a little bit about that in a second. You can go very far in this direction, and when these slides are posted, you can look at that link or Google it. It's some research out of Stanford, and we know other companies have done this. This idea of megakernels, you take the whole model and you just write raw GPU code to execute it. There's no abstraction, like clean abstractions and stuff in it, and torch abstractions. You just write the C++ code, it just does the whole model. And this one, in theory, is, in their blog post, is 1,000 tokens per second plus for Llama 1B, which is significantly beyond where we are. So it's very powerful. It's just, its impact is limited to lower batch sizes and so on, so we don't really personally invest in it. But it is interesting. Beyond Fusion, Fusion is like the most basic kernel optimizations you can do. Beyond that, there's a lot of opportunities to just write better algorithms. And you can, if you spend any time online, you'll find a lot of versions of it. Flash attention is probably one of the most well-known ones, where they optimize the attention operation, and then they optimize it further in version 3 for the newer capabilities of NVIDIA's, the newer hardware. There's fast sampling kernels that we use. You can also just take the existing kernels and you can tune them in smart ways for the models and the hardware that you care about, which is where we kind of had an advantage, because for us, we're not trying to solve the general problem that the LLM or NVIDIA or so on are trying to solve, where we have some core models that we care about, we have some core workloads that we care about, and so we can really make those go fast, even if we have to make trade-offs with other workloads we don't care about. But like I said, custom kernels aren't easy. And I have a lot of war stories I can talk to you about very popular kernels and stuff having very subtle bugs. This is one of them. So we spent weeks trying to figure out why one of our servers was sporadically crashing. And it turns out that it was a bug in a very well-known sampling kernel. And it was only triggered when the final layer of the model produced one hot vector, which is pretty hard to reproduce just based on the inputs. And when it did that, there's a loop within the kernel that turned into an infinite loop, because they were doing an exact inequality with 2 floating point numbers, which had just happened to be lower precision than they needed for that loop to terminate. And so this was something that, like, these are subtle, very subtle bugs that crop up. And this is a very complicated kernel. They got the complicated part of the algorithm, really, they nailed that. But this, like little bugs like this do crop in. We've seen lots of small issues like this. But switching gears a little bit, I talked a little bit about model compression being necessary, right? These models are very big. Why is it necessary? It's necessary partly because of the competitive landscape, right? Like if you're going to host Llama 4, for instance, right? It is up against Anthropic's Claude, it's up against other model providers, and within that landscape, you absolutely have to compress this model to get within the economic, like this dollars per token that you need to be in, and the right performance. And when you can compress the weights, that gets rid of a lot of the memory bottlenecks. You can do the compute in 8 bits as well, which gives you additional flops, basically, because you've got twice as many matrix multiplications, but roughly you can do. We have not, you can go further. There's lots of people that go down to 4 bits. Theoretically, I think the latest research is, about 3 bits is where you start losing in an ideal world model quality. But we've found enough challenges even going down to 4 bits, and the speed ups aren't really worth it. So we tend to stay, balance it out at 8 bits. If you do this wrong, it's very easy to slow down the process. Like you're going for better performance. You compress weights. If you don't use compressed compute, you basically are upscaling, downscaling so much, it just wastes enough time that your system becomes slower. What's much more troubling is it's very easy to degrade model quality. There's like at least 3 or 4 common, very common quantization schemes that folks use. And if you just flip those flags in something like VLM, it's very easy to end up with something like this. So this is a real example from Llama 8B running in, I believe, TensorWise FP8. And you just go to it, you say, hey, tell me a very long story. And it's fine for like 1,000 tokens, and then it just devolves into gibberish. And if you're running a basic vibe check on this system or something, you're not going to see this. Because what's happening is errors are accumulating, and you get to a long enough context, and it just throws, like you hit an edge condition, and the model basically just falls over. This is not, you can go into Playground, you can put this prompt into our 8B. This is not what it does. It tells you the actual story, because we did the work to make the FP8 quantization work. So yes, so this is the lesson I would like to leave you with is, you need to quantize with care. We think about looking at quantization schemes that, quote unquote, are quality neutral. We carefully select them. We look at layer activations, a large spread of benchmarks, and so on. And we've developed new kernels to actually maintain quality, which do hybrid computation. Like some of it is in higher precision, some of it is in lower precision. So you kind of thread the needle between getting better performance, but not degrading quality. So that's quantization. Remember, calling back to something I said earlier, which is there are very strong economies of scale here. Like you want to concentrate a lot of servers, a lot of users on heavyweight hardware. Like it's better for all of us to share H100 than each of us to get like our own A10, roughly, which is a much, all of us would get better performance. Now that starts to break down when folks have fine-tuned models, right? You can't, it's different weights. And so we spent a lot of time figuring out how to share servers with fine-tuned models. And this is sort of, this technology underpins AI, the agent bricks. Now, I'm not going to spend a lot of time talking about it, but just want to give a high level. We use this idea of training smaller adapters that live with the models. It's a pretty common technique. But when we started to implement it, we found that the popular ways of doing it actually caused quality issues. And so we spent a lot of time with our research team finding a version of it that maintained the quality that we needed, which was very slow out of the box. So we spent a lot of time as a performance team trying to optimize it with things like those parallel paths and so on, and custom kernels. There have been a couple of talks at the conference that go much deeper into this. So I would point to them, and when the slides and stuff are released, videos are released, I would encourage you to look at them if you're interested in this. What I will say is, I don't have enough time to talk about all the optimization work that we do. I will say I have a very firm belief there's a lot more headroom. And some of it is data-driven, some of it is intuitive. I think we have another 2x, 3x, so on to go. And beyond that, GenAI is a very fast-evolving space, right? Like you're getting new models every month, new techniques, new hardware coming online. So what users you should expect is the cost and performance of these models to just improve. Quarter over quarter, year over year, you should expect significant improvements. But as performance is increasing, it's very important to pay attention to quality. Quality is a lot more important than performance. Some inference runtimes that are out there are very, very good at producing gibberish very, very fast. And we have used them in production. We've had to deal with some of these issues. It's hard to detect. It's hard to detect during releases if you don't have a good release process. It's hard to debug. Sometimes it's obvious, like the gibberish example I shared with you. Bad FP8 quantization, you'll start vibe checks start failing. You start seeing coding mishaps and so on. Other times it's much less obvious. So this is a bug. This is a real bug from a Llama 4 implementation, where it's applying the nonlinearity on the wrong side of a matrix multiplication. So that's a pretty big difference in the math. And this is in a core component. Now, the way this manifests is the human eval score goes down by 5 points, which is, OK, I don't really know how to debug that. You dig into what's happening, there's one line difference in this whole generation that it has. And most of the generations are not affected. And so especially when you start getting to these larger models, they're surprisingly resilient. And so small bugs are not going to show up in vibe checks, end-to-end evals. You have to do much more thorough testing and evaluation. And so we've built this system for very strict quality control over the last few quarters. And the idea that every release we have, whether we're releasing something that's open source or inbuilt or something, has to go through a gauntlet of tests. And it has to go through a range of academic evals, where we then have to analyze the differences between the release and the prior release, based also correct for statistical differences in these evals, then look at the layer like very deep statistics on layer activations and stuff. And then just the usual stress tests, evals, unit tests, like all that other stuff. I raise this because for folks that are running at scale, there's a very great thriving LLM inference ecosystem. There's amazing work coming out of that. But if you want to operate at scale, you have to, have a foundation of basically very good CI/CD behind it, because you can't just take their releases and put them into production. There's a lot that can go wrong, and even if you have standard CI/CD, you have to extend it with this more Gen AI specific version of it. Okay, so that kind of brings us to the end of the talk, 2 minutes before it's supposed to end. What I want you to take away from this is that on the Databricks model serving team, we're focused on delivering this high quality, high performance experience, and we're also doing a lot of deep work to continuously improve that. We're very excited about what our users are building with these things. Foundation model endpoints, they underpin a lot of our features. As a company, we're sort of more on the agnostic end of like, hey, if you want to use Anthropic, well, yeah, we'll help you use that. It's more about data intelligence, right? It's less about, we're not a Gen AI company. We're not really pushing our own models. But in a lot of cases, these open weights models are the right tool, especially when they're fine-tuned. And so we have to make them sort of fly. If you want to try out how well all the stuff I talked to you today about is working, go into Databricks, click optimize on an endpoint, see how well it does. Run some AI functions in SQL. Play around with the foundation models in the AI playground. And yeah, excited to see what you all do with this. And yeah, that's the end of my talk.